Welcome back to Terminal Bash. In this episode, we are going to be covering common collections. So, in common collections, Rust Standard Library includes a number of very useful data structures. Most other types of data types represent one specific value, but collections can contain multiple values. Unlike the built-in type or built-in array and tuple types, the data these collections point to is stored on the heap. So arrays and tuples are stored inside of the stack. So the amount of data does not need to be known at compile time and can grow or shrink as the program runs via the allocation of memory from the OS. Okay, each kind of collection has different capabilities and costs, and choosing an appropriate one for your current situation is a skill that you'll develop over time. I'm sure that's true. In this chapter, we'll discuss 3 collections that are used very often in Rust programs. So this is where we touch on vectors that allow you to store a variable number of values next to each other. A string is a collection of characters. We've mentioned the string type previously, but this chapter we'll talk about it in depth. And a hash map, the good old hash map you use to allow a value with a particular key. This particular implementation of the more general data structure is called a map. Okay. To learn about other kinds of collections provided in the standard library, we'll look at the documentation. All right. So, the first collection type we'll look at is vector T, known as a vector. Vector allows you to store more than one value in a single data structure that puts all the values next to each other in memory. Vectors can only store values of the same type. Thus, we specify the type here. They're useful when you have a list of items, such as lines of text in a file, or the prices of items in a shopping cart. To create a new empty vector, we call vecNew function as shown in listing 8.1. All right, so let's go ahead and get into Git, into the Rust book, and we are going to probably cargo create, cargo new, and we're going to call it chapter are we on? Chapter 8, common collections. 8. And you know what I'm going to do? I'm going to reorder some stuff here. So I'm just going to make a directory called chapter 8, common collections. And then inside of here, we'll create our crate, cargo new, and it will be creating vector. And then we can cd into there, and now we can modify our files. Okay, so let v type vec of type integer 32, which is a signed integer. So let a vector equal, or vector of type vec I32, capital V. There we go. Equals vec new. Okay. Okay, so now we can print line our vector. Okay, so back into the chapter 8. We are going to, what do we want to do? Cargo run. and we get an issue. Cannot be formatted with default format. We have to say : question mark, which I'm still fuzzy on what that is, but I know it works. Okay, so here we can see we've got our empty vector. All right, and so now, for now we know that vec t type provided by the standard library can hold any type, but it can only hold the same types. And when a specific vector holds a specific type, the type is specified within the angled brackets. And that's generics. And that's how you specify types into generics. So vector is a generic implementation. Yep, so we told it was an signed integer. Sorry, no. Unsigned. Yeah, signed integer, I think. In more realistic code, Rust can often infer the type of the value you want to store once you insert values. So you rarely need to do this type annotation. Cool. It's more common to create a vec t that has initial values, and Rust provides the vec exclamation macro for convenience. The macro will create a new vector that holds the values you give it. Okay. So let's try a couple of things here. So if we say vector is equal to vec exclamation, and then inside of square brackets, we provide it 1, 2, 3. And then we'll have vector 2. Okay. We run that, and we see both of those. Can I not provide a variadic list of ints? No. I'd have to look up the vector API, which it's going to give me now. So we can vpush. So if I were to vector push 1, can push take multiple? It cannot. Okay. So now we've got, what's the complaint? Vector mutable. Let mute vector, and then we can push. Okay. And we can see that those are fundamentally the same. And we can print line, we'll say this. If vector is equal to vector 2, print line equality. So unnecessary parentheses. Cool. Okay, so you can compare vectors to each other directly as a type comparison, and even though they were created with one with the macro and one with pushes, they are fundamentally the same, even though one is not mutable. Right? If we want to change its value, we need to make it mutable, which we knew. Dropping a vector drops its elements. Like any other struct, a vector is freed when it goes out of scope, as annotated in listing 8.4. When the vector gets dropped, all of the contents are also dropped, meaning those integers it holds will be cleaned up out of memory. This may seem like a straightforward point, but can get a bit more complicated when you start to introduce references to elements of the vector. Let's tackle this next. Okay, so now that you know how to create, update, and destroy vectors. Knowing how to read their content is a good next step. 2 ways to reference a value stored in a vector. In these examples, we've annotated the types of the values that are returned from these functions for extra clarity. Listing 8.5 shows both methods of accessing a value in a vector. Okay, indexing syntax or get. So, get by the number or get by the index. So, let's just do this. So we want to print line. We have to do this. And inside of here, we want to print vector 1 and vector.get 1. Or we'll say 2. And let's mix these up. So we want to push these in reverse order. So we will say if we get 1 here, we expect it to be, if we do 0 here, we expect it to be 1. If we say 3, we expect it to be 3. And that should pretty well illustrate our point. Okay, so what's the complaint here? Doesn't implement, cannot be formatted. That's interesting. Let's see what we get when we run this. 3, none. Get, is that index value? Sum 1. Oh, interesting. So get returns you a sum, and sums have to be pattern matched against, which means if I were to, okay, this has interesting implications. So if we were to replace this with 3 and then reference 3 here, and we'll reference 2 here, we should get an out of index error. Thread main panicked, index out of bounds. Yeah. The len 3, but the index is 3. So that's very interesting because if I reference get, then I will be returned none instead of sum, which means in the pattern matching, I can, well, you could even have potentially a bad for loop written, and while getting is not none, ooh, let's do that. Okay. For do we have while? I forget. Let's look at loops. Wow. Okay. So while, you know, we will need a for actually. For let. Let's see. For element in vector we'll just print line the element. I think we'll have to do it like this. Let's try that out. Okay, so we get that, and if I recall, Rust for loop iterator. I don't think it has it. Processing a series of items with iterators. Yeah, so it's the iterator trait. on all of this stuff, so you don't even construct a for loop like that. For x in range, yeah, so it's just a fundamentally simpler for, which I'm a-okay with. So let's see. Nope, I'll need that documentation for later. All right. So I'm not really sure if I would need get at that point. I mean, if ever it was in a scenario where I wanted none rather than an out of bounds exception, you would use the safety of get. So, two details here. First, we use the index value 2 to get the third element. Vectors are indexed by number starting at 0 like everything else. Second, two ways to get the third element are by using ampersand and just a square bracket, which gives us a reference, or by using get method, which passes index. So third, we want to pull out a reference to 2, which means if we were to modify it, it should modify. I'm going to leave that for now. Get method with the index passed in as an argument, which gives us an option of a reference of the type. Rust has two ways to reference an element, so you can choose how the program behaves when you try to use an index value that the vector doesn't have an element for. As an example, let's see what a program will do if it has a vector that holds 5 elements and then tries to access an element at index 100. Yeah, we already did this. Cause a program to panic because it references a non-existent element. Get past an index that is outside the vector, it returns none without panicking. You'd use this method if accessing an element beyond the range of the vector happens occasionally under normal circumstances. Your code will then have logic to handle either some reference of an element or none, with pattern matching as discussed in Chapter 6. For example, the index could be coming from a person entering a number. If they accidentally enter a number that's too large and the program gets a none value, you can tell the user how many items are in the current vector and give them another chance to enter a valid value. That would be the most user-friendly, or more user-friendly than crashing the program due to a typo. Couldn't agree more. Couldn't possibly agree more. Okay. When the program has a valid reference, the borrower checker enforces the ownership and borrowing rules, covered in Chapter 4. To ensure this reference and any other references to the contents of the vector remain valid, recall the rule that states you can't have multiple mutable and immutable references in the same scope. The rule applies in 8.7, where you hold an immutable reference in the first element in the vector and try to add an element to the end, which won't work. Okay. So yeah, this reference, you push, it's going to say error, v, can't borrow v as immutable, because it's also borrowed as immutable, which is here. Yep. So we would first have to release this, the borrowing of it, before we could continue. The code in listing 8.7 might look like it should work. Why should a reference to the first element care about what changes at the end of the vector? The error is due to the way vectors work. Adding a new element onto the end of a vector might require allocating new memory. Okay. And copying the old elements to the new space. If there isn't enough room to put all the elements next to each other where the vector currently is, In this case, the reference to the first element would be pointing to deallocated memory. Borrowing rules prevent programs from ending up in that situation. We'd love to whiteboard that. Iterating over the values in a vector. If we want to access each element in a vector in turn, we can iterate through all the elements rather than use indices to access one at a time. Listing 8.8 shows how to use a for loop to get immutable references to each element in a vector of I32 and print them, which we did. We didn't get a reference though. We just iterated over it. Okay, but if we get a reference, we can then make it mutable and we can map. Basically, we can iterate over them. The for loop will add 50 to each element. To change the value that the mutable reference refers to, we have to use the dereference operator, dereference, to get the value in I before we can use the plus equals operator. We'll get into that in chapter 15. At the beginning of this chapter, we said that vectors can only store values that are the same type. This can be inconvenient. There are definitely use cases for needing to store a list of items of different types. Fortunately, the variants of an enum are defined under the same enum type. So when we need to store elements of different type in a vector, we can define and use an enum. Okay. So let's say that we get values from a row in a spreadsheet in which some of the columns in the row contain integers, some floating point numbers, and some strings. We can define an enum whose variants will hold the different value types, and then all the enum variants will be considered the same type, that of an enum. Then we can create a vector that holds the enum and so ultimately holds different types. We've demonstrated this in 8.10. I'm not going to look at 8.10. I am going to try to do it myself. So we'll cd up and we will cargo new a enum of vector of enums. Okay, and then inside of main we will have a struct called users, and the user will have a name that's a string. They'll have, we'll say, first name, last name, phone number, and that'll be, we'll say, an integer, I32, and what else will a user have that's not an integer? We'll say logged in, and that will be a bool. Okay, and then we're going to have our vector. So let's define this struct in the module. Hope I'm getting that terminology right. Or the crate. Either way. So we'll let a vector, or we'll say users. Users is going to be a vector. Now, I want to specify it here. I know I could use the macro, but I'm not going to. I want it to be a vector of users. And that didn't seem super happy. And that will equal a vec new. and then we'll say user 1, let user 1 and user 2 equal, so this would be users, which means on line 1, this should actually just be user. User is going to be John, and this would be name first name, John, last name will be Doe, phone, this is an I-32, 555-555-5555, and logged in will go ahead and be false. And then for the next user, this will be his wife, Jane, and her number will be 555-555-5554, and she will be logged in. She will be logged in and set as true. All right, and then in our type, let's go and zoom in, users, we can push user 1 and user 2. And then we can go ahead and print line and say, what is users? Okay, let's try that out. Cargo run. Okay, so we have an error. So these have to be different kind of string, right? So this has to be string from that. Same here, string from okay. So now we have to adjust that to the type as defined above, and it's still not happy. There we go. And now it's unhappy about us printing users. User doesn't implement debug, right? Which is required. I'm just going to go ahead and implement that, and I don't fully remember how. So I have to look up restlang implement debug. It's like an annotation. Yeah, okay. So we derive debug. So now it does. Cannot borrow as mutable, right? Because always got to think about mutability when we're doing these. So let mutable user be that. And then the phone number out of range for 32. So we can go ahead and switch this to, let's do an unsigned. That shouldn't be out of range. Is it? Let's do an unsigned 64. Okay. There you go. So now we have on this line users, which is a vector of users, a vector. See if I can highlight it. Vector of user. And inside that user is John Doe, logged in false. And then we have another user who is Jane Doe, and she is logged in. And then you end your vector. Okay. That makes perfect sense. So I'm going to go ahead and we'll go back to our book and we'll skip over. They did the vector helper or macro, that is. I opted not to do that, instead forcing my variable to be mutable. Alright, now that we've discussed some of the most common ways to use vectors, be sure to review the API documentation for all the many useful methods defined on vector in the standard library. For example, in addition to push and pop, push a pop method removes and returns the last element. And I imagine that would be somewhere inside of here, vector. We got examples, indexing, slicing, capacity and reallocation, guarantees, and methods. So here's a new method, and they show us as mutable. Here we can say construct a new empty vector with the capacity. So it'd be vec with capacity. Yep. From raw parts. Creates a vector directly from the raw components of another vector. Not sure what that means yet. Returns a number of elements in the vector. Reserves capacity for additional more elements to be inserted into the given vector. The collection may reserve more space to avoid frequent reallocations. After calling reserve, capacity will be greater than or equal to the self.length plus additional. Does nothing if capacity is already sufficient. Reserve exact is like reserve, but exactly what you want. Nightly only experimental API tries to reserve capacity for at least the additional more elements to be inserted. Collection may reserve more space. After calling reserve, or try reserve, capacity will be greater than or equal to self length plus addition. Does nothing. Capacity is already sufficient. Okay, and if it overflows, or the allocator reports failure, the error is returned. How is that different than reserve? Panics if the new capacity overflows. Okay. So this will try reserve here, and then pre-reserve the memory existing for can. Now we know this can't out of memory in the middle of the complex work. Okay. Okay, I got it. Shrink to fit. Okay. We'll drop down. Yep, that's great. Shrink to a certain size. Into box slice. Converts the vector into a box. Which we're going to get to boxes. Not going to go ahead. Jump on that yet. Truncate shortens a vector, keeping the first length elements and dropping the rest. As slice extracts a slice containing the entire vector, equivalent to &s. Okay. Get a mutable slice. Has a pointer, new raw pointer to the vector's buffer. The color must ensure that the vector outlives the pointer this function returns, or else we'll end up pointing to garbage. Modifying the vector may cause its buffer to be reallocated, which would also make the pointer invalid. That sounds sketchy. Mutable pointer. Set the length unsafe. We haven't learned about unsafe yet. And there's just a ton. There's our pop. Append. Moves all the elements of other into self, leaving other empty. So drain creates a draining iterator that removes a specified range. There's just an absolute ton here. So could spend I feel like a lifetime on this page. All right, let's move on. Storing UTF-8 encoded text with strings. We talked about this in Chapter 4, but we'll look at them in more depth now. New rustaceans commonly get stuck on strings for a combination of 3 reasons. Rust's propensity, that's a good word, for exposing possible errors, strings being a more complicated data structure than many programmers give them credit for, and UTF-8. These factors combine in a way that that can seem difficult when you're coming from other programming languages. It's useful to discuss strings in the context of collections because strings are an implementation of a collection of bytes. Plus, some methods to provide useful functionality when those bytes are interpreted as text. In this section, we'll talk about the operations on a string that every collection type has, such as creating, updating, and reading. We'll also discuss the ways in which a string is different from other collections, namely how indexing in a string is complicated by differences between how people and computers interpret string data. Okay. What is a string? We'll first define what we mean by the term string. Rust has only one string type in the core language, which is the string slice str. This is usually seen in its borrowed form as reference str, or borrowed string. In Chapter 4, we talked about string slices, which are references to some UTF-8 encoding string data stored elsewhere. String literals, for example, are stored in programs binary and are therefore string slices. The string type, which is provided by Rust's standard library rather than coded into the core language, is a growable, mutable, owned UTF encoding string type. When rustaceans refer to strings in Rust, they usually mean the string and the string slice, which is the borrowed string types, not just one of those types. Although this section is largely about string, both types are used heavily in Rust's standard library, and both string and string slices are UTF-8 encoded. Rust standard library also includes a number of other string types, such as OSString, OSString, str, CString, and CString. Library crates can provide even more options for storing string data. See how those names all end in string or str? They refer to owned and borrowed variants, just like string and str. These string types can store text in different encodings or be represented in memory in a different way. For example, we won't discuss these other string types in this chapter. See their API documentation for more about how to use them and when each is appropriate. So, creating a new string. Many of the same operations available with a vector are available with a string as well, starting with the new function to create the string, shown in 8.11, as well as from. This line creates a new empty string called s, which we can then load data into. Often we'll have some initial data that we want to start the string with. For that, we use the toString method, which is available on any type that implements the display trait, as string literals do. So this is a string literal. it must implement the display trait as specified, and then we can take it to a string. So this initial contents to string also works on literal directly. Okay, so that seems to be the same as string from, but let's find out. We can also use the function string from to create a string from a string literal. Code in 8.13 is equivalent to the code from 8.12. So it really becomes preference. Because strings are used for so many things, we can use many different generic APIs for strings, providing us with a lot of options. Some of them can seem redundant, but they all have their place. In this case, string from and toString do the same thing, so what you choose is a matter of style. Remember that strings are UTF-8 encoded, so we can include any properly encoded data in them. Anything properly encoded with UTF-8. Okay, to update a string can grow in size and its contents can change, just like the contents of a vector, if you push more data into it. In addition, you can conveniently use the plus operator or the format macro to concatenate string values. We can grow a string by using pushString method to append a string slice. So we've got a mutable string from foo, and we can push string bar onto it. And that's a string slice, I suppose. Figured it would be a literal, maybe they're the same thing. After these two lines, S will contain foobar. The string push method takes a string slice because we don't necessarily want to take ownership of the parameter. For example, the code in 8.16 shows that it would be unfortunate if we were able to use S2 after appending its contents to S1. So we create a mutable S2 or S1, then we create S2 and we push S2 into S1. We say S2 is S2 if we weren't able to. Okay. Takes a string slice because we don't necessarily want to take ownership of the parameter. If the pushString method took ownership of S2, we wouldn't be able to print its value on the last line. However, the code works as expected. The push method takes a single character as a parameter and adds it to the string. Okay. Okay, so it takes essentially a rune. So we're not passing ownership. Got it. Got it. So concatenating and format macro, create strings, add them together, we have a new string. So these are O of N operations. I would believe, anyway. The string S3 will contain hello world as a result of this code. The reason S1 is no longer valid after the addition, and the reason we use a reference to S2, has to do with the signature of the method that gets called when we use the plus operator. The plus operator uses the add method whose signature looks something like this. You bring in yourself, which I guess would be S1, and a reference to a string S2, which is why we have to do a reference. Yeah. Makes sense. This isn't the exact signature. Oh, and it also said S1 is no longer valid because we passed in S1 to this function, and when this function exits, it clears out S1 from memory and kills the pointer. So let's demonstrate that real quick. So let's do this. we're going to cargo new a, what do we call it? Invalid pointer. Okay, so cd into invalid. And then we'll mess with source main. So now, if we print line, and we want to print S2, and then S3 and S1, and we cargo run, we get an error here, aborting due to 3 previous errors. Let's find out what they are. We did not put our appropriate commas. Okay, so immediately it tells us borrow of moved S1 value borrowed here after move. So if I delete, that should be good. Yep. So it's just letting me know right away that we can't do that. And if I try to run it, it'll tell you, hey, value borrowed after move. Okay. And I'm actually going to leave that there. For future reference. Okay. Makes sense. The string S3 will contain hello world as a result of this code. This isn't the exact signature that's in the standard library. In the standard library, add is defined as generics. Here we're looking at the signature add with concrete types substituted for the generic ones, which is what happens when we call this method with the string values. So we'll get to generics later. Okay. The reason we're able to use S2 in the call to add is that the compiler can coerce string argument into a borrowed string. And when we call to the add method, Rust uses a deref coercion, which here turns reference S2 into reference S2 and the entirety of the string. We'll discuss deref coercion in chapter 15. Because add does not take ownership of S parameter, S2 will still be a valid string after this operation. Very good. Second, we can see the signature of the add takes ownership of self. Yep, we know. Boom, boom, boom. At this point, tic-tac-toe with all of the plus and quote characters. It's difficult to see what's going on. Okay, and then you can use format to get an easier read on it. So if we were to do this, and we will just say cargo new format example. And now if we were to print line and we want to say S1, 2, 3, and actually we will do S itself. So the format operator does not take ownership. Does this. So I'm just going to copy paste. So, oh, it does. We'll delete the remainder of that line. Does it? Does it not? Let's try. There we go. Yeah. So S, because it's the same concept that we just ran into above here for string add. Yeah, it's this. So it's going to take ownership of S1 and then get rid of it. So I would almost, in that ideal, just reference format if you ever wanted to preserve ownership of S1 within your scope. Okay. Indexing into strings. Okay, so in many programming languages, accessing individual characters in a string by reference of the index is common and valid. However, if you try to access parts of the string using index syntax in Rust, you'll get an error. Consider the invalid code. Trait bound index is not satisfied. Cannot be indexed by integer. The error and the note tell the story. Rust strings don't support indexing. Why not? To answer that question, we need to discuss how Rust strings are stored in memory. A string is a wrapper of a vector of unsigned 8-bit integers. Let's look at some of our properly encoded UTF-8 example strings from listing 814. So if we get the length of this, it'll be 4. But what about the following line? Note that this string begins with a capital Cyrillic letter ZE, which is this, not the Arabic number 3. Okay? Asked how long the string is, you might say 12. However, a Rust answer is going to be 24. That's the number of bytes it takes to encode the string in UTF-8, because each Unicode scalar value in that string takes 2 bytes of storage. Therefore, an index into the string's bytes will not always correlate to a valid Unicode scalar value. To determine or demonstrate, consider this invalid Rust code. What should the answer be? Should it be the ZE letter? When encoding UTF-8, the first byte of ZE Cyrillic letter is 208. The second is 151. And so answer should in fact be 208. But 208 is not a valid character on its own. Returning 208 is likely not what a user would want if they asked for the first letter of this string. However, that's the only data that Rust has at byte index 0. Okay, users generally don't want the byte value returned, even if the string contains only Latin letters. They wouldn't want 104. Well, talk to Go, they do that, and you're right. To avoid returning an unexpected value and causing bugs that might not be discovered immediately, Rust does not compile this code at all and prevents misunderstandings early in the development process. Cool. Bytes and scalar values and grapheme clusters. Oh my. I need to Google that. Grapheme. The smallest meaningful contrasive unit in a writing system. A rune. Okay. Another point about UTF-8 is there are actually 3 relevant ways to look at strings from Rust's perspective. There's bytes, scalar values, and grapheme clusters. The closest thing to what we would call letters. If we look at the Hindi word written in Devanagari, I don't know, script, it is stored as a vector of unsigned 8-bit integers. Values that look like this. So 1, 2, 3, 4 characters take 18 bytes. Yep, okay. And that's how computers ultimately store this data. If we look at them as Unicode scalar values, which are what Rust char type is, those bytes look like this. Okay? There are 6 char values here, but the 4th and the 6th are not letters. They're diacritics that don't make sense on their own. So in other words, this gets added. Yeah, so this gets added on top here, and this gets added on bottom here. Looks like. No, that's not right. Where does it get added? I don't know about that one. Oh, it does get added to that. Interesting. Finally, we'll look at them as graphene clusters. We'd get what a person would call 4 letters that make up the Hindi word. Got it. I feel like this one is missing the graphene cluster, and this one is not. Rust provides different ways of interpreting the raw string data that computers store so that each program can choose the interpretation it needs. Got the whole workflow up and running on Docker and GitLab. Dude, I'm good. I'm glad. Very glad about that. How hard was it? Was it not too bad? A final reason Rust doesn't allow us to index a string is to get a character is that indexing operations are expected to always take constant time of 1, but this isn't possible to guarantee that performance with a string. Silly nuances. Every system has them. Every system has them. Good perseverance, though. That's what we need. Does Go have some clean, like no coalescence operator? Well, I'm doing Rust right now. I'm not sure if Go does. No coalescence. Yeah, I'm not sure. Because Rust would have to walk through the contents from the beginning of the index to determine how many valid characters there were. Inline if else. Oh, I see what you're saying. I think you're talking about a ternary. No, I don't think Golang does have ternaries. Yeah. As pointed out, and hopefully unsurprising, if else is indeed the idiomatic way. Yeah. Rust ternary. Because the no coalescing, yeah, this is what I'm used to seeing. Ternary uses that. It's a binary operator that is part of the syntax of the basic conditional expression in several programming languages, including C#. Yep. So, like, what does PHP do for theirs? Yeah, this gets turned into this. This is what I'm used to seeing for no coalescence. Does JavaScript have null coalescence? Oh, it does. Null-ish. Let's ignore JavaScript. Let's get to something strict. Yeah, possibly null value, value if null. Yeah. This is what makes the most sense, and I don't think Go has null coalescence. In fact, we would know here. It does not, and Rust does not either, which is a bummer. But Rust, I get why Rust doesn't, because they have pattern matching. Yeah, that's null coalescence. Ternaries are a little different, and Go has neither. And it looks like Rust doesn't have either. Oh, wrong section. Okay. So indexing into a string is often a bad idea because it's not clear what the return type of the string index operator should be. A byte value, a character, a grapheme cluster, or a string slice. Therefore, Rust asks you to be more specific if you really need to use indices to create string slices. Okay. Byte at index 1 is not a char boundary. It is inside of this. Okay. You should use ranges to create string slices with caution because you can, or doing so can crash your program. Okay. Understood. Methods for iterating over strings. Fortunately, you can access elements in a string in other ways. Yep, for in chars. So if you need to perform operations on individual Unicode scalar values, the best way to do so is to use the chars method. Calling chars on a string in Hindi separates out and returns 6 values of type char. And you can iterate over the results to access each element. And that's where you end up with this. That does not take in grapheme. The bytes method returns each raw byte, which might be appropriate for your domain. And then, yeah, snipped. Strings are not so simple. To summarize, strings are complicated. Different programming languages make different choices about how they present this complexity to the programmer. Rust has chosen to make the correct handling of string data the default behavior for all Rust programs, which means programmers have to put more thought into handling UTF-8 data upfront. This trade-off exposes more complexity of strings than is apparent in other programming languages, but it prevents you from having to handle errors involving non-ASCII characters later if you're in your development lifecycle. Okay, I'm not sure how a 4 over Hindi and getting this as an output would be very helpful, but apparently it is. Okay. Storing keys with associated values in hash maps. And is this the last in this chapter? It is. And then we're on to error handling. Okay. The last of our common collections is the hash map. The type hash map key value stores a mapping of keys of type K and values of type V. It does this via hashing function, which determines how it places these keys and values into memory. Many programming languages support this kind of data structure, but they often use different names, such as hash, map, object, hash table, dictionary, or associative array, just to name a few. Yeah, and we're just going to call them hash maps, which is what it is. Hash maps are useful when you want to look up data, not by using an index, as you can with vectors, but by using a key that can be of any type. So, for example, in a game, you could keep track of each team's score in a hash map in which each key is team's name and the values are each team's scores. Given the team name, you can retrieve its score. But if you were to want to analyze scores or group scores, you'd have to iterate over each item in the hash map. We'll go over the basic API of hash maps in this section, but many more goodies are hiding in the functions defined in hash map key value by the standard library. As always, check the standard library documentation for more information, which you didn't link to. Okay. Creating a new hash map. You can create an empty hash map with a new keyword or new function and add elements with insert. We're keeping track of scores of two teams whose names are blue and yellow. The blue team starts with 10 points and the yellow team starts with 50. So let's do this. So we're going to cargo new hash maps. And we'll just edit this. So first things first, we're going to use from the standard collections, just a hash map? A hash map. Okay. And then we'll create a mutable, we'll create an mutable scores variable. Sure, we'll do that up here. Let mutable scores equal what? A hash map new. Okay. And then inside of main, we can insert the scores. Scores dot insert, and then strings from blue. From blue. And then the score, which I think is 10, and 50 for yellow. Okay, and then we can print line as a macro, and we'll say like this, scores. And then down here we can just cargo run. We expected item. Let mutable scores hash map new. Oh, yeah, that's right. Maybe it really wants it in there. Okay, so there we got blue and yellow, each at 50. All right. Note that, what was that error? Expected item. Cannot compile, could not compile hash maps. Expected item found keyword let. Okay. Just like vectors, hash maps store data on the heap. This hash map has keys of type string and a value of I32. Like vectors, hash maps are homogeneous. All of the keys must have the same type, and all of the values must have the same type. Another way of constructing a hash map is to use the collect method on a vector of tuples, where each of the tuples consists of a key and its value. The collect method gathers data into a number of collection types, including hash map. For example, if we had the team names and the initial scores in two separate vectors, we could use the zip method to create a vector of tuples where blue is paired with 10 and so forth. Then we could collect the method to turn the vector of tuples into a hash map, as shown in 21. So we created a team vectors, blue and yellow teams are there, and then we create a vector of 10 and 50. We create a hash map where we specify whatever type gets past 10, and then we iterate over the teams and zip them, and we pass the initial scores in, and that combines them, and then we collect them into a hash map as defined on the left side of the equal for scores. The type annotation hash map with the underscores is needed because it's possible to collect into many different data structures, and Rust doesn't know which one unless you specify. For parameters, For the parameters of the key and value types, however, we use underscores, and Rust can infer the types of the hash that the hash map contains based on the types of the data in the vectors. But it doesn't have to be that way. So we're going to do we're going to cargo new hash map zip. Okay. And then inside of here, we can say that we know that this is going to be a string, and we know that this is going to be a unsigned 32-bit integer. Oop. And then we run it. Oh, now we get errors. All right. So what is it mad about? A collection cannot be built from an iterator over elements type string and integer. Reference of integer. Integer. Collection of type string 32 cannot be built from string or std iterator item string and integer. Okay, I'm not sure how. I guess we just have to rely on them for the moment. Unused variable. So print line colon question mark scores. And then we can cargo run that. And there we go. Okay. Hashmaps and ownership. For types that implement the copy trait, like integer 32, the values are copied into the hash map. For owned values like string, the values will be moved. Okay. Will be moved, and the hash map will be the owner of those values. We weren't able to use variables field name and field value after they have been moved into the hash map with the call to insert. Okay. Values, accessing values in a hash map. We can use get to get them out as long as we use a reference. Here, score will have the value that's associated with the blue team, and the result will be sum reference 10. The result is wrapped in sum because get returns an option of a reference of the type. If there's no value for that key in the hash map, get will return none. The program will need to handle the option in the way that is covered in Chapter 6 with match syntax. We can iterate over each key value pair in a hash map in a similar manner as we do with vectors using a for loop. Okay. Although the number of keys and values is growable, each key can only have one value associated with it at a time. When you want to change the data in a hash map, you have to decide on how to handle the case when the key already has value assigned. If you replace the old value with the new value, completely disregarding the old value, you could keep the old value and ignore the new value, only adding the new value if the key doesn't already have a value, or you could combine the old and the new value. Overwriting. Insert to the same, push scores, the original value of 10 is overwritten. Or insert instead of insert, we'll see blue is 10, yellow is 50, blue is 10. Using the entry method, scores entry or insert. Using the entry method to only insert if the key does not already have a value, or insert method on entry is defined to return a mutable reference to the value of the corresponding entry key if that key exists, and if not, inserts the parameter as a new value for this key and returns a mutable reference to the new value. This technique is much cleaner than writing logic. Ourselves, in addition, plays more nicely into the borrow checker. Running code on 825 will present 50 and 10. First call to entry will insert the key for the yellow team with value of 50. The yellow doesn't have a value already, so 50 becomes a value. Second call to entry, it will not change the hash map because the blue team already has a value 10. Okay, so to update, we create a hash map, we create some text, we create a mutable map of the hash map. For text, split white space, so for every word in the text, let the count, it's going to be entry, word, or insert 0. So okay. How does that make sense? The code will print world 2, hello 1, wonderful 1. The or insert method actually returns a mutable reference to a mutable v type to the value for its key. Okay. And then we increment it. Got it. So it's 0 at first. 0, this is the reference to the value of word. And then we increment it, and we have to dereference count, which means word, which is the key. Where's map in this instance? Map entry word, which is the value of that entry, would then get moved to 1, 2, 3, 4, 5, etc. That's cool. So we'll always get a mutable reference when we try to do entry or insert. So this is just a clever way to get a default value, but we definitely do want the reference to the word. It just might be 0. Almost wish this was .default, but whatever. This code will print as we expect. The mutable reference goes out of scope at the end of the for loop, so all of these changes are safe and allowed by borrowing rules. By default, Hashmap uses cryptographically strong hashing function that can provide resistance to denial of service attacks. This is not the fastest hashing algorithm available, but the trade-off for better security that comes with the drop of it in performance is worth it. If you profile your code and find that the default hash function is too slow for your purposes, you can switch to another function by specifying a different hasher. A hasher is a type that implements the build hasher trait. We'll talk about traits and how to implement them in Chapter 10. You don't necessarily have to implement your own hasher from scratch. Crates.io has libraries shared by other Rust users that provide hashers, implementing many common hashing algorithms. Vectors, strings, and hash maps will provide a large amount of functionality necessary in programs when you need to store, access, and modify data. Here are some exercises you should now be equipped to solve. Given a list of integers, use a vector and return the mean, average value, median when sorted, the value in the middle position, and mode, the value that occurs most often. A hash map will be helpful here. Okay, convert. So these are things I should do. I probably won't do them tonight, but I should do them. Convert strings of Pig Latin, or to Pig Latin. The first consonant of each word is moved to the end of the word, and A is added. So first becomes erstfe. Words that start with a vowel have hey added to the end. Apple becomes apple hay. Okay. Keep in mind details about UTF encoding. Using a hash map and vectors, create a text interface to allow a user to add employee names to department in a company. For example, add Sally to engineering, add Amir to sales, then let the user retrieve a list of people in the department or all people in the company by department, sorted alphabetically. I'm going to make a whole nother stream on these. So another benefit of what I did here is I can do a README. So touch README. And in the README, we can say chapter 8. We are going to do a coding challenge stream. And that will be this list. So cool. Okay. So that summarizes that. Was that the last little bit of this? I do believe it was. All right, cool. Standard library API documentation describes the methods, vectors, strings, and hash maps that will help or be helpful for these exercises. We're getting into more complex programs in which operations can fail, so it's a perfect time to discuss error handling. And we will do that next time on the Rust programming language book here on Terminal Bash. It's been an absolute pleasure. Thanks for joining for the stream. I might be streaming a little bit more a little later tonight, but for now, I'm going to say goodbye, and I'll see you next time.